and understanding the long-term aging of these materials. And since we are material scientists, we are trying to establish the link between micro and nanostructure to macroscopical properties, either optic, mechanics, or etc. So as you understand, this is multidisciplinary, multi-techniques as well, and multi-scale. This is for studying the morphology, the microstructure, and the chemical nature of cultural heritage materials. But today I will do a highlight on our expertise in electron microscopy, especially TEM and CEM, and associated techniques. This because we are part of ERIS since very recently, and I wanted to present you some aspects of this the team and what we can do. So we have a lot of people that are involved in the service, microscopy service, that can do preparation of lamellas and the different techniques associated to transmission electron microscope. So we have 6 transmission electron microscopes with different sources and different detectors. And we have an expertise as well in different networks, the French network called METSA and the European one called STEAM. So to illustrate what we can do, so the first case is the Chinese ceramics case. When we look at black glazed giant wares from the Song dynasty, we can see that there is a lustrous glaze, black and to brown, and it presents unique color patterns due to the organization and nature of crystals. So in these crystals, they are mainly iron oxide phases. Sorry, there is an echo. Okay, and among these phases, we found mainly the rare polymorph called the epsilon phase, and among, of course, different phases. And to understand the growing mechanisms of these iron phases in the glaze, we decided to have a look at the nanoscale of these different small crystals. So to prepare the lamella, we have done what we call FIB, focus ion beam. This is the way to prepare thin lamella, one of the way. This is done in this SEM that I show here, the Thermo Fisher Helios Nano Lab. And in this SEM equipment, we can do different steps. The first one is to deposit the platinum area to mask the area of interest. In this case, we have placed the platinum mask on top of the dendrites that are inside the crystals. And after that, we can etch around this with gallium ions to create a kind of pools, and from which we can extract this thin lamella with a micro manipulator. And after this step, we can thin down to around 100 nanometers. So it has to be transparent to electrons. And in the right-hand side, in the bottom, you can see a microscope image of the dendrites. This is a cross-section from the bulk to the surface. Of course, the first step in this case is to do EDS analysis to get the elemental maps of these crystals. So as you can see here in one of the dendrites, we can find a lot of iron, aluminum, titanium, magnesium, and they are in different proportions. But in order to understand which crystalline phase they are with, we have to do different techniques. So we did 2 techniques to get the crystalline phase. The first one is the automated crystal orientation mapping, also called in the field 40 STEM. On this technique, we are acquiring different electron diffraction patterns with a CCD camera by doing scanning along these dendrites. And by comparing with the database, it's possible to identify the different phases. So in this case, we could find the epsilon phase, the hematite, the spinel phase, and pseudobrochite. So as you can see, the step is around 10 nanometer, so with very good resolution. Another technique that was used was TKD, or called transmission Kikuchi diffraction. This is based on the inelastic diffraction, and that produces Kikuchi lines, as you can see on the image. And this is done in the same equipment. So this is it's equivalent to EBSD for those who know, but with transmission instead. So although the step is a bit larger, around 25 nanometers, we are also able to get the different crystalline phases. So these two techniques, although with different acquisition, allow us to reveal the phases that are inside these crystals. Sorry. I didn't show you here, but there was an orientation study as well to get the epitaxy relationship between the different phases and to understand how they are produced and at what stage of the manufacturing process they are produced. So this is the first case. And the second case that I wanted to show you is the protective coatings on historical aircraft. So, as you may know, aircraft constitute a very large heritage field. There are a lot of aircraft in museums or kept with associations, and they are generally kept outdoors because they are large artifacts. And as you can see in some of them, there are problems of corrosion and, of course, alteration in long term. So in some of them as well, we can find the original paintings that was produced at the time. And this is an aspect that we found very interesting because the protective coatings at the times, they experienced a lot of development. There was the beginning of the chemical industry, and we have a lot of different processes applied on the materials of these aircraft in order to protect them against corrosion. In this sense, it could be, for instance, anti-corrosion of aluminum alloys being the main materials for building this aircraft. So here you can see on the Morane-Saulnier from the post-World War aircraft, the original painting on which we could find a specific primer. So the primer being the first layer that is deposited on top of the metal to allow adhesion and anti-corrosion properties. And in this primer, this was what we call the wash primer, a mix of pigment, zinc chromate-based pigment with polyvinyl resin and phosphoric acid. And this was developed after World War II. And it was proved to be better than the only pigment mixed with resin that was used before. The question we had is it what type of reaction it produces when we deposit this type of wash primer on top of the aluminum? And the second question was, is it still efficient after 80 years of aging outdoors? Can we say that the primer is still doing its role of anti-corrosion? So to understand what was the reaction produced, we had to do multi-technique approach, and two of them was absorption spectroscopy techniques. So for this, whether with X-ray or with electrons, there are absorption techniques such as the XAS or the EELS that can produce very fine structures around the absorption edge of elements. And these fine structures are characteristic of chemical bonds and the environment of the atoms. So this can give an information on the element, the chemical composition of the primer. The difference between the two techniques is the fact that we are working at different energies. One is on the, around 2 to 10 kilo electron volt, and this is done with a synchrotron source. And while the other that I'm going to present you today is an electron source, so in a CEMES microscope, and it's a much lower energy. But this is complementary because we can reach different type of elements, lighter elements in the case of EELS, or different edges of elements. Of course, the probe size as well is different. In the case of the synchrotron source, we are around 0.3 to 0.7 microsquare, whereas for the electrons, we are more in the angstrom of resolution. So this is very good to probe the pigments in these different forms, because we can recognize oxides, carbonates, phosphates, etc. So as this presentation is mainly on TEM, we'll just say that we did preliminary study or acquisition in ESRF on the ID21 line in order to get the Xanes spectra across the layers that I have shown you before, to understand what type of chromate we had. And as a matter of fact, this historical primer that contains the pigment is showing here black on the black curve, a typical, well, not a typical actually a spectrum, but a spectrum which is between a chromium 6 as shown in the green spectrum, and chromium 3 which is in the blue. So this, with this conclusion, we can say that our historical primer contains a mix of the original pigment, which is a chromate, and some different chromium 3 plus compound for which we don't know the origin. So that's where TEM comes to of interest, because it's complementary. And I'm going to show you quickly that for doing this, we did a different lamella preparation. So for preparing the samples, we need to embed the sample in a resin, polish thinly to thin down the two sides, and to do ultramicrotomy to get the slices of the cross section. So this was done in the historical primer to get here, as you can show, as I can show you, the different cross section, the aluminum alloy, the primer, and with the different techniques we can get a nice picture of the image of the pigment. Of course, we can do EDS on this pigment to recognize where the elements are located. And for the STEM EELS technique, I show you a typical spectrum that we can get for the chromate-based compound. With oxygen and chromium and phosphorus at the edge. In the case of the historical primer, these are the curves that we obtained, and this is done after treatment. And we could see that we are suspecting actually a mixture of chromium phosphate and zinc phosphate in the layer. So this is helping us to understand the different reactions that took place during the deposition of this primer at the origin, when they were mixing the zinc chromate with the phosphoric acid. So this is very short view of what we can do. I wanted to show that advanced STEM and the association techniques can be very useful for nanoscale investigation of cultural heritage materials. Preparation of thin lamella is a key point. It could be very tricky, but by doing this and coupling, of course, with other techniques, we can get a full view of these complex materials that are most of the time not very homogeneous. But this is very interesting in terms of multi-scale study. So I thank you for your attention, and I've put the link of the catalogs where we are here for in the IRIS service. Thanks a lot.